Welcome back to our series on multivariable calculus. In this episode, we're going to talk about motion along a curve. In particular, we're going to go all in on these space curves representing the motion of a particle. This lecture will feel very much like a physics lecture because we're going to be talking about the analogy that the space curve vector indicates the trajectory of a particle in space. Okay, let's begin with a little bit of review for the derivation we're about to do. The first piece of review will be for our unit tangent vector. The unit tangent, of course, pointed along the direction of the curve and had a magnitude of 1. So it's based on r prime divided by the magnitude of r prime. That guaranteed that its length was 1. Next, let's review curvature. Curvature was a scalar rather than a vector, and it was basically the ratio between the magnitude of the unit tangent vector and the magnitude of the velocity, r prime. Remember, the curvature was a scalar that told us how sharply the function curved while moving at a rate proportional to the arc length. The final piece of review is actually a vector we could have covered in the last lesson, but it was running a little long. It's a vector very similar to the unit tangent vector. It's called the unit normal vector. And the unit normal uses the symbol n, and very much like a plane's normal that points perpendicular to the surface, the unit normal vector has a length of 1 and is always perpendicular to the unit tangent vector. Namely, it always points towards the direction that the function is curving. So it's strongly related to both the curvature and the unit tangent vector. In order to calculate it, of course, it's a vector, so we want the derivative of the unit tangent vector and then divide it by that magnitude. Now you might question why we're dividing a unit tangent vector by its own magnitude. Keep in mind the unit tangent vector has a length of 1, but its derivative may be elongated or shortened. So once again, we have to normalize it by dividing it by its own magnitude. In essence, the unit normal vector will always point perpendicular to the curve, and in general, as you'll see, it always points towards the direction the function is curving. But again, it has a magnitude of 1, so it's useful for its direction rather than its magnitude. Okay, with that review out of the way, let's begin our derivation. What we're going to do now is talk about an interpretation of r of t, our space curve, which remember is just defined in terms of 3 functions that represent the 3 components, ft, gt, and ht. Except now we want to consider it exclusively as the path of a particle through space as a function of time. Well, let's look at its consecutive derivatives because they have an interesting physics interpretation. Most of what I'm going to cover now will make more sense to you if you've already encountered a good introduction to mechanics course, namely two-dimensional kinematics, which I imagine for students in a 3rd semester of calculus, you've probably already experienced some introductory physics. So much of what I say will be review to you, but the derivations will necessarily add some interesting context to the physics you already know. Well, the first derivative of the position function we know to be the velocity function, and we've been describing it this way all along. Well, let's reinterpret it in terms of some of the definitions that we have above. R prime of t is v of t, and so solving for it means this would be equal to the magnitude of v prime times the tangential vector. Now let's interpret this and see just what it means. The magnitude of the velocity, of course, is the size of the velocity vector. It's the magnitude of r prime of t. And of course, t is the tangential vector. It defines the direction of the curve at every point, and it does so with a length of 1. So if we take the magnitude of the velocity times the direction the velocity will be, which is always tangential, you can see why this is a good interpretation of the velocity vector. Remember also that these are each independent functions of t. Basically, the unit tangent vector as well as the speed will both be functions of time. Well, now let's look at what would be the next derivative, r double prime of t, which we can interpret to be the acceleration vector, which of course will be the first derivative of the velocity vector. And of course, we can calculate that directly because we now have a function representative of the velocity vector. Well, remember, these are both functions of t, so taking the derivative means applying the product rule. So this will be the magnitude of v prime times the tangential vector plus the magnitude of v times the derivative of the tangential vector. And that's just applying the product rule to this function here. Again, two independent functions of t that happen to be multiplied, and I want the derivative. Well, this right here is really interesting. We're going to rewrite this in a couple of ways. We'll leave this first term alone because that's not the one that really needs major changes to it. So it's v prime times the tangential vector plus, and here's where I'm going to start doing some rewriting. The first thing I want to replace is the derivative of the tangential vector. We'll see that that's over here as part of the normal. And if I solved for it, then the derivative of the tangential vector would be equal to the magnitude of the tangential vector's derivative times the normal. So this would be v times the magnitude of t prime times the normal vector. Well, we can go one step further. The definition of curvature features the magnitude of the derivative of the tangential vector in its numerator. So I can solve for that. That would be equal to r prime, which is the velocity, magnitude of it, times the curvature. So we can rewrite this one more time. V magnitude prime times the tangential vector plus, and then I'm just going to replace that with the curvature times the magnitude of the velocity. So that'll make the magnitude of the velocity squared times the curvature. So it's curvature times the magnitude of the velocity squared times the unit normal vector. Well, that's it. We're done with our derivation. Now let's spend a little time interpreting this. What it appears is that the acceleration vector, the second derivative of position or the first derivative of velocity, is in two independent components. That is, one component runs along the direction of the curve. And of course, its coefficient is the derivative of the velocity. That is the rate of change of velocity. That makes sense. I'm going to reinterpret this. I'm going to call the magnitude of the velocity, the derivative of that, the derivative of the speed. And of course, that would be the tangential component of the acceleration. By tangential component, I mean the degree to which the acceleration influences the magnitude of the velocity. It's very possible for the acceleration to influence the velocity by increasing or decreasing its magnitude. But the only portion of the acceleration that would be responsible for that is the acceleration that shares a component in the tangential direction. If the acceleration has no component tangential to the curve, that means the space curve has a constant speed. That is, its velocity's magnitude won't change. And we've seen some curves that were that way. We've seen curves that had constant tangential speeds with zero tangential acceleration. Well, let's look at the second part of the curve. The second part of the acceleration is the curvature times the magnitude of the velocity squared. And it's in the normal direction. We'll call this AN, that is the normal component of the acceleration. And of course, it will point normal to the curve. Turns out the direction of the normal always points towards the interior of any curve. So if something is curving towards the right, that means the normal points interior. And this is the degree to which the acceleration influences the direction of the curve. Remember, velocity can be accelerated in two ways, by changing its magnitude through the tangential component, or by changing its direction through the normal component. If we drew a space curve for a straight line, its normal component would be 0, because if it never turns off of that straight line, it can't ever have a component of the acceleration that's perpendicular to the path. Any straight line motion, one-dimensional kinematics, would feature a 0 value here. Now, Many of you are already familiar with tangential acceleration. After all, that's sort of the normal acceleration that you see that's part of one-dimensional kinematics. This would be the entire acceleration for 1D kinematics. But anytime you do 2D kinematics, you always feature accelerations that turn. And we've already had a name for that turning acceleration. We called it the centripetal acceleration, AC. And we already knew that it had a magnitude of v squared over r. That is, the magnitude of the centripetal acceleration always went as the square of the velocity divided by the radius. Well, let's see why that is consistent with our definition of AN, which, by the way, is the centripetal acceleration. One geometric interpretation for curvature that we never looked at is this. If this represents a function, RT, and we're interested in the curvature at this point and at this point. Well, one geometric interpretation of curvature is if I draw a circle that is tangent to the circle, a circle that is tangent to the function at that point, then its radius's relationship to the curvature is as follows. The curvature will be equal to 1 over this radius. And if we solve for the curvature at that point, that's what we'll find out, is that the curve at that point matches a circle whose radius is r, then the curvature will be the reciprocal of that radius. Here, of course, the circle would be much larger in order for its curvature to match, and therefore the radius would be larger, and therefore the curvature would actually be much smaller. A larger radius will produce a smaller curvature, and a smaller radius will produce a larger curvature. With curvature being interpreted geometrically as 1 over the radius of the curve at that point, notice what that does to our AN. If AN is numerically equal to the curvature times the magnitude of the velocity squared, and we can interpret curvature as 1 over the radius, then there it is. The component of the acceleration that points normal to the curve is mathematically equivalent to our centripetal acceleration. Now, all of this interpretation is just a way for you to understand how these components work out. Finding the velocity and acceleration from our original space curve is nothing more than taking consecutive derivatives. Because while we've gone through the argument that r prime of t is the velocity, which is equal to this function, and that r double prime of t is equal to the acceleration vector, which is ultimately equal to this function, we can also interpret that v of t is just going to be the first derivative of the original space curve, f prime t, g prime t, and h prime t. And further, that the acceleration is simply its second derivative. So at would be equal to f double prime t, g double prime t, and h double prime t. The derivations we did here is just a way to interpret what the meaning of the velocity and the acceleration are in terms of our unit vectors that are tangential and normal to the curve. Hopefully this gives you some greater insight into the physics that you already understand, and in particular to the evaluation of centripetal acceleration, why it was that the centripetal acceleration was always proportional to v squared over r. This can be seen as a pretty good proof of that.